In the previous lecture, we looked at finite automata, which is a rather restricted model of computation. And in this lecture, we're going to contrast this by the most powerful model usually considered in theoretical computer science, namely that of Turing machines. It is by now widely accepted that anything that a modern computer can do can be done also by a Turing machine. But the model of a Turing machine is significantly simpler than that of a modern PC or tablet, say. And this makes it easier to analyze its computational power. We saw that one example of the rather restricted computational power of finite automata was this language here. No finite automaton would recognize this. And the reason for it can intuitively be seen in the fact that finite automata have a fixed finite amount of memory. And for recognizing this language here, you would have to have a variable amount of storage or memory available, because what you would have to do to recognize this language was just read the input, count the number of zeros at the beginning, store this number, and then once you start seeing ones, you just count the number of ones that you read against that counter that you stored before. But this needs to be a variable size counter, because n is going to differ for different words in the input, right? So a finite automaton having only finitely many states can not recognize this. You might say that a real computer also has only a fixed finite amount of memory, let's say 4 GB. But the idea is that we can always go ahead. If we need, we can extend the memory, and we can buy a bigger hard drive, or we can use several computers that then together compute a task. So the idea is to come up with a model that has potentially unlimited amount of storage. And that's the basic idea of a Turing machine. A Turing machine has in common with a finite automaton that it has only finitely many states. But now you should think of those states as a program, where each state represents a line in the program. But in addition to this, a Turing machine has a memory, or often called work tape, on which the machine can read and write. So that's the significant difference. This seems much closer to the way we picture a computer these days, so that of a CPU operating on some memory and executing all kinds of instructions there. So that's also the idea behind a Turing machine, namely that a program which corresponds to the CPU operates on some work tape by reading and writing entries on that work tape. Before I give a formal definition of a Turing machine, I would like to give a brief graphical drawing of its basic components. I think from that you can get the basic structure of a Turing machine much more easily than from the formal definition, which is a little bit abstract, just as in the case of finite automata, I think. So here we have the tape of a Turing machine. It's bi-infinite, so infinite in both directions, and that, as I said already, is capturing the idea that we can add memory as necessary. Some authors define the tape of a Turing machine as infinite only in one direction, but it can be shown that from the point of view of computational power, those two versions are equivalent. The tape itself is divided into infinitely many cells, and these cells can hold entries from a finite alphabet, or a special symbol B that is assumed not to be in the alphabet A, that symbolizes the blank symbol. So just saying that there's nothing stored in that cell. So if, for example, we assume that our alphabet is binary, as usual, with the symbols 0 and 1, then the cells can contain either 0, 1, or they can have a blank symbol. Furthermore, a Turing machine has a read-write head. I'll depict it like this. And this read-write head always points to one cell. So I'll mark it as this way. And the idea is that this read-write head performs operations on the current cell according to a finite program. So operations are very simple. It can either read the current symbol, it can write a new symbol, or it can move the read-write head left or right. The program itself is just a list of instructions, and you can think of these instructions as similar to the instructions of a finite automaton, namely given by a transition function. Now let's look at the formal definition of a Turing machine. So first we have a set of states. Call them again Q. And as in the case of finite automata, this set of states is finite. This corresponds to the fact that in a computer or an algorithm, the number of instructions or the length of a program is finite. Just as in the case of finite automata, there are two designated states, special states. One is Q0, the initial state, and the other one is QF, the final or halting state. Note here that our halting state is only a single state, not a set of states, as in the case of finite automata. So then we have the alphabet, A, which is again finite, and a special symbol, the blank symbol, B, that is assumed not to be in A. And finally, we have the transition function that is a mapping delta from that maps a state and a symbol. So think the current symbol that is pointed to by the read-write head, and that cell can contain either a symbol from A or the blank symbol. So depending on both those entries here, it maps to a symbol. So think of what I want to write, depending on what I've read, a new state, and a direction. So D stands for direction, and that's the direction I want to move the read-write head to. And this direction can either be left, right, or stay where you are. So what does it look like now to run a Turing machine on an input? So we assume we have an input from our alphabet. So W is a string over A. This string will be written or copied onto the tape of a Turing machine here, and each cell holds one entry from our input string W. To the left and the right of this string, the tape contains blanks. So B, 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 and so on. So in both directions we have infinitely many blanks. The read-write head will initially be placed on the first blank symbol to the left of the input. So this cell here. Furthermore, we set the current state of our machine to be equal Q0, which you remember was the initial state. And all of this together, so initial state, initial configuration of the tape, and the position of the read-write head, forms the initial configuration of the Turing machine. So a configuration of a Turing machine will always be a snapshot of the work tape together with the position of the read-write head together with the current state. So snapshot of a tape plus current state. That's a configuration of the Turing machine. And this here describes the initial configuration. So this is what the Turing machine looks like when it's starting to run on this input. How does a computation step of a Turing machine now look like? Suppose we have the current configuration given. So think of it as a snapshot of the current contents of the tape and the position of the read-write head and the state. So in particular, I know the current symbol that is read or pointed to by the read-write head and the current state of my program. And then I can look up the transition function for this, namely delta is a function of the state and the symbol read. And the value of this transition function is a triple ydp, where y is an entry from the alphabet or the blank symbol, d is a direction, left, right, or stay put, and p is a state. So the idea would be to say, well, if I am currently in state Q and read symbol X on the tape, at the position that my read-write head points to, then replace the symbol X by symbol Y, go in direction D or left, right, or stay put, and enter a new state P. So for example, assume this would be our current state of the tape, and the current state would be 3. And this, again, is the snapshot of the tape, where this is the symbol currently read by the read-write head. Then we would have to look up delta for 3, 0, because 3 is the current state, and 0 is the symbol currently read. And assume that the value of delta for 3, 0 is 1, right, and 5, then this would mean that we would replace the current entry 0 by 1, move the read-write head by 1 position to the right, so over here, and go to the new state 5. So new current state equal to 5. So it should be clear now that we can iterate this this step. So we can now, giving the new current state and the new snapshot that we have, we can apply this procedure again and again. So does this procedure ever stop? Well, we say that the Turing machine halts if we ever reach state QF. Remember, that was the special state designating the final or halting state. Well, that might of course never happen, but if it does, then we say that the Turing machine outputs the string, and that's a string over A, the string that is on the tape immediately to the right of the current cell. So what does that mean? Well, if this is the configuration of the tape, when we reach the final state, QF, then we would take the string that is immediately given to the right of the current cell. So here we would have the current cell, and the A string immediately to the right of it would be the string 0, 1, 1. And here we have the first blank, and that's not a symbol of our alphabet A, so it would not be included in the output, and the output would just be 0, 1, 1. Note that the output is always a finite string over A, and the reason for that is that in order to reach QF, we only pass through a finite number of configurations, so a finite number of steps, and we start out with a finite number of symbols from A on the tape. The input is a finite string, and in each step of computation that we pass through, we can write only one additional symbol, right? At most one additional symbol. So that means in the course of a computation, we can add at most finitely many additional symbols from A to the tape. So that means in either direction, I will always reach a point where from that point on, I will read only B's. So blank symbols from that point on. That means our output, which is a string over A, is always a finite string. So this concludes the basic definition of a Turing machine and the description of how a Turing machine runs or computes on an input. In the next lecture, I'll go over an example to really give you a good idea of how this works in detail.